Okay, so welcome back again to this course Advanced Manufacturing and Process Modeling. So I am back with the first module of the course. So in this module we will as I told you earlier, we will discuss about the different manufacturing processes. We will briefly introduce them, and also we will introduce the different modeling techniques that we generally follow to simulate these processes and to grab insights of them, and also we will discuss about the mechanics involved in those techniques of process modeling. So the manufacturing processes, they can be broadly classified as two. One is processing operations and assembly operations. So even in processing operations, we can further classify as primary processing and secondary processing. So what are the primary processing techniques? So the primary processing techniques are like casting, powder metallurgy, additive manufacturing. So these are the techniques where we can get the component directly from the manufacturing processes, and the secondary processes, example is machining. So where we have to also example is forming. So where we have to work with the already processed preforms, and then we need to rework with them, and then so that we can achieve the final desired dimensions of the part. So in case of assembly operations, we can also differentiate it as permanent joining processes. You can see over here, and also we can classify as mechanical fastening. So permanent joining is like welding, brazing, adhesive bonding, etc. So you in our daily life you might have seen several examples of welding and brazing. Brazing, it is very common, it is there in our TV sets. You can see the motherboard of your computer also. There is a solder joint, brazed joints you can see in plenty, and also the mechanical fastener is the riveted joint that some of you I am sure that you have traveled by aircraft. So you can see the wings of the aircraft, there you can see the rivets. So these are basically the different manufacturing processes. So we will start with the one of the most ancient and basic manufacturing process, that is casting. So what is metal casting? So metal casting is of course a science. It also an art, because it allows the engineers to develop the desired parts in near net shape, and with the desired geometrical perfections of the cast part. So what is the beneficial in case of casting is its immense design freedom. So you can basically cast any shape of you want to, if you can, of course if you can design the die effectively. So so in casting there are couple of aspects. Number one is the material aspect, where you need to prepare the melt appropriate way so that it is free from defects, and so that you can get the sufficient structural integrity in the developed cast parts, and also their mechanical properties as per the desired level of attributes. And apart from material aspects, there is a important geometrical aspect. Geometrical aspect is with the design of the mold cavity, and also the getting arrangement of the mold, like for example the runner and the sprue, down sprue and the ingate, all these dimensions should be appropriate. Of course we will discuss in detail about the design aspects in further when we progress further with the course. So so with this introductory part, we will I will briefly tell you what are the different parts of a casting mold. So if you assume a sand mold, so this is basically the top part, we call it as the cope part, and the down part of the mold is called the drag part, and this is the parting line which separates the cope and drag hub of the mold. And then this is the pouring ladle, where from we pour liquid melt into the mold cavity. This is the sprue, and this is the sprue base well, and this is basically the region where the melt enters the mold cavity, the component cavity. It is called the ingate. So so you can see this is the cast part after taking it out of the mold. So this is the solid casting, and this is the sprue which is needed to be trimmed. So this operation of taking the getting geometry out after we cast the metal piece is called basically the fettling operation, where we can take them out. So, based on the mold cavity, choice of mold cavity, also we can classify casting processes like permanent mold casting, like shell mold casting, and also investment casting, where we use ceramic shell in that case in spite of using sand. And also in terms of the process, speed of the processing technique, and we also classify like metallic mold based casting processes as die casting, which can be further classified as high pressure die casting and low pressure die casting. And even based on the chamber temperature, we can classify die casting as cold chamber and hot chamber die casting. So, other processes are like plaster mold casting, centrifugal casting, etc. Okay. So, so then we will move to the forming processes. So, we will introduce metal forming processes now. So, there are several metal forming processes that we generally follow in engineering practice. So, they can be classified as rolling, drop forging, press forging, extrusion, and so on. So, in case of rolling, what we basically we can classify it as two different rolling techniques based on the temperature. They are called hot rolling and cold rolling. So, hot rolling, essentially we do the rolling beyond the recrystallization temperature of the metal involved. So, recrystallization temperature is what? It is basically, in general, we define recrystallization temperature of material as it is basically 0.5 of the melting temperature of the particular metal which is involved. So, when we are doing the rolling processing, the rolling temperature T roll, if it is greater than 0.5 Tm, then we can call it as hot rolling. And then when we are doing that rolling temperature is less than 0.5 Tm, then we can classify as cold rolling. So, here there is a catch. So, we also sometimes talk about another process which is in between the hot rolling and cold rolling. So, we call it as warm rolling. So, when we generally roll the metal or the alloy specimens close to the recrystallization temperature, but it is well above the room temperature, we call it as warm rolling. So, it combines the individual advantages of both hot rolling and cold rolling processes. We will discuss in detail in subsequent sections of this course. So, the applications of rolling process is production of sheets, strips and structural components, and then drop forging. It is one of the basic forging technique that we generally use. So, in this case, a workpiece which is placed between a die set and a heavy hammer is dropped to deform the material into the die shape. So, it is a one of the primitive forging technique. So, the advantages are high production rates, enhanced mechanical properties due to grain refinement, and the some applications are automotive components such as connecting rods, crankshafts. These are being developed by drop forging route. Okay. And then there is press forging. So, press forging is also a technique where we are basically applying pressure over the ingot which is placed within the die cavity, forging die. But the difference with drop forging is that in this case we apply the pressure gradually with the help of hydraulic or mechanical press, rather than applying instantaneous pressure like we do in case of drop forging. So, accordingly there are some advantages that it offers over drop forging, like precise control over deformation, better dimensional accuracy than drop forging, and the applications are aerospace components and several other mechanical parts. So, then we will move to the offset forging. So, offset, it is basically it increases the cross sectional area. So, what we do in case of offset forging, we basically apply a hammer blow. It is quite similar with the drop forging process. So, here what happens that in case of offset forging, we basically increases the cross sectional area and we decrease the height of the metal ingot. But I mean, in often there is a problem that we encompass in case of offset forging, that is called the barreling effect that we see because the because of the flow of the metal towards the peripheral direction. So, to avoid that, we have to design the die in a appropriate way, so that we can retain the dimension of the desired component or part after undergoing offset forging. So, the applications are fasteners and valve components, and then we will talk about extrusion. So, again in extrusion, based on the temperature, we can classify it as hot extrusion and cold extrusion. So, what we basically do in case of a extrusion die, so if there is a metal piece which is applied being extruded through this opening, and the metal piece after being extruded, it is going in the direction of the application of the force, then we call it as forward extrusion. And then if in the other case, like in case of if the ram which is applying pressure, that is hollow, there is a concentric hole in the ram, then the metal piece can go at the opposite direction of the ram movement. So, then we call it as backward extrusion. So, this is also another classification that we can consider in case of extrusion. So, there are many applications of extrusions like tubes, rods, and complex profiles like heat sinks. The extrusion is largely being applied for development of heat sinks, for various applications of thermal management. And then we move down to wire drawing. So, wire drawing is another metal forming technique which is very popular to develop metal rod or wire. So, it is quite similar with extrusion, only the difference is in this case there is a drawing head which is connected with the metal piece rod which is getting drawn. So, this is, so you can assume that this is the drawing head that pulls the that rod which is going out of the opening of the die cavity, and thereby basically we are getting the wire with the desired diameter. And also of course, because of extreme work hardening that takes place in the material because of wire drawing process, we often get fine grain morphology, higher dislocation density in the drawn rods, and also we get significantly improved mechanical properties in the drawn wire rather than the original feedstock, original ingot that we are using for wire drawing process. So, the advantages of wire drawing process are precise control over diameter and improved surface finish, and the applications are electrical wiring, suspension cables, and fasteners. So, and then here comes the sheet metal operation. So, this is the for kind of forming technique that we encompass in our day to day life. There are several sheet metal fabricated components that we use in our daily appliances, in our home, in our offices. So, there are common sheet metal forming technique such as bending or shearing or deep drawing. The applications are, like I told you, it is used in automotive panels, it is used in home decoration, and also several other office furnitures. So, these are some example of sheet metal operations, and there is other so these are the different solid state forming processes that I have discussed until now. So, there are some benefits associated with solid state forming processes compared to the liquid state processing, that is casting, that I just discussed before this. So, the benefit is because here in this case the wastage of the material is much lesser. Because in this case the like in casting I discussed that we need to remove the different non-functional part, non-functional after solidification. The mold geometry, the gating geometry, they are the functional part during casting. So, they need to be removed. So, that causes a lot of wastage of the raw material. But that kind of problems are often not that severe in case of solid state processing route like metal forming techniques that I have discussed until now. So that is another that is a major thing, that is material efficiency. And the second is mechanical properties, because in case of metal forming processes, we because we are basically doing deformation processing, so there is a preferential flow of grains that takes place. A classic example of that can be a crane hook that we many of us have seen. So here we basically do not, we can manufacture it by casting also, but we do it by metal forming basically to achieve preferential flow of grains, so that we can achieve much higher mechanical properties in this case. So that is another reason why we go for metal forming, to improve mechanical properties. And also there is economical aspects, which is it is suitable for high volume. So these are the different metal forming techniques. And now we will move to the fabrication, joining techniques. So of course, like other manufacturing processes, even metal joining has several variants. What are those? Like gas welding, resistance welding, resistance pot, resistance seam, electric arc welding, and so on. Now if I discuss about them one by one. So in case of gas welding, we generally use oxyacetylene torch. So we generally use it to heat and melt the workpiece and filler material if we are using filler material. So gas welding can be done in both the occasions, using filler or without using filler material. So the features are, so the applications are repair work and joining thin steel sheets and pipes. So you might have seen this oxyacetylene gas welding in many of your daily appliances also, like you might have seen the works with your the home grills and all. Often they are gas cutting or gas welding techniques are being used to join different parts. So but that is not that much industrially viable, because nowadays much improved techniques have been evolved of welding where we can establish more precise control. And also what is the problem, major problem that we see in case of welding is that because of the heat generated, intense heat generated locally, where we are basically trying to achieve the weld joint. For example, this is a typical bar joint between two plates. So if we try to do by gas welding, so we often end up not by able to control the heat affected zone of the this weldment. So but however, when we are dealing with like arc welding techniques or resistance welding techniques, then we can have a precise control over the heat affected zone. That means we can control the microstructure of the weldment post welding. So that causes, so this is basically the weld zone. So that is why we can achieve much improved mechanical properties in other advanced welding routes. So what are they? So we will now discuss briefly, like electric arc welding. So here in this case, this welding technique employs an electric arc to generate intense heat for melting the base and filler. So so these are the classifications are tungsten inert gas welding, metal inert gas welding, and also manual metal arc welding. So here based on the so here you can see one interesting thing. So there in MIG welding, the electrode we are using which is a consumable electrode. So that means that also serve as a filler material, and it gets deposited in the weld bed, and it is part of the weld pool formation. Whereas in case of tungsten inert gas welding, it is a non consumable electrode. So in this case, the electrode does not melt in the process, it does not get consumed during the welding process. So that is a major difference between these two techniques. And also welding techniques can also be classified based on whether we are actually using a filler material or we are not using filler material. So when we are not using any filler material, then that welding we call as autogenous welding, and when we use filler material, so then we we classify it as a normal welding technique. So the advantages are high strength joints and suitable for various metals and thicknesses. So then we move to the electric resistance welding. So often in electric resistance welding is it is autogenous welding in many occasions, or otherwise it is a homogeneous welding. I mean, when with the filler material and the base material is of same chemistry. So, I mean, it generates heat at the interface of two materials by passing an electric current through them under pressure. So, the variants are spot welding and also the seam welding. So, when basically there are two plates. So, if they are placed in say I mean lap configuration, and then we can create a bead because of the electric current passed through that, then we can call it as resistance spot welding. And then when we get a series of beads, then we can call it as resistance seam welding. So, these are the I mean different classifications of the electric resistance welding processes. The applications are I mean automotive body panels, manufacturing of pipes and containers, etc. And the advantages are it is very fast and highly automated, and it can produce clean joints with minimal deformation. And then here comes the thermite welding. So, thermite welding is very interesting. So, it is basically can be classified as a mini I mean casting process. So, here you can see that often the thermite welding process we can see in case of railway tracks, because I mean this is also the technique which is invented much before the electric resistance welding processes, because there I mean that there can be the I mean railway tracks in the location where there is, may not be electricity available nearby. So, there I mean basically it is a chemical process. The heat is generated because of the chemical reaction, and because of that intense heat the I mean the filler material, which is often in close chemistry or compositionally close to the base metal, is being melted, and then it basically filled within the I mean joint which is prepared between both the work pieces. And so, this is a case of thermite welding. So, the features are there is no external power source is needed. That is what I have discussed, suitable for heavy duty applications. So, of course, railway tracks are I mean a classic example for heavy duty application. And so, yeah, and then we will move to the I mean cold welding I mean processes. So, in this case basically the primary mechanism of achieving the joint between two adjacent metal plates is basically the diffusion. So, here the bonding is achieved through pressure without the application of heat. So, it requires clean and smooth surfaces for effective bonding. Why it is so? Because if we have to join two I mean pieces, then if we do not have the clean surfaces, then there won't be atomistic bonding possible between the clean surfaces. So, so the first prerequisite that they must be in contact to each other and the surface must be clean to facilitate atomistic level bonding I mean at the onset of applied pressure, so that diffusion can take place between the I mean material A and material B, and then they can fuse together. So, this is the example of cold welding, and so typically used for soft metals like aluminum and copper, and the applications can be used for joining of dissimilar metals and also for electrical connections. So, advantages are because we are not using intense heat to prepare the weld joint. So, that is why there is not much distortion or residual stresses generated in case of cold welding processes. So, the summary of the characteristics. So, heat application, some processes like gas and arc welding rely on heat, while others like cold welding rely purely on pressure and they are diffusion driven. And I mean because of the pressure mechanical bonding takes place. I mean so, strength of joints, welding produces the strongest joints, while soldering and brazing are suitable for less demanding applications. So, as I told you that earlier that we can see the soldered and brazed joints in many of the electronic circuitry, where I mean they are very much sensitive to the temperature. So, we can only use the soldering or brazing I mean techniques which is dealing with the low temperature I mean fillers, and the applications are fabrication processes which are essential across industries like automotive, construction, electrical and electronics. So, welding is a very versatile technique. It has I mean it has been being applied everywhere. I mean all the I mean frontiers of industries, because I mean only thing is it is a technique which develops permanent joint. So, if the if the that particular engineering component or is allows for permanent joint formation and doesn't need to be the joint doesn't need to be disassembled later on. So then welding is the best available technique for joining. However, when there is a there is a chance or tendency to disassemble the parts and that joint is only temporary nature, then it is it is advisable to use mechanical fasteners like rivets to achieve the temporary joint to achieve the assembly. So, with this we will move to the material removal processes. So, this is basically a classic example of subtractive manufacturing technique. So, in material remove machining techniques, we the basic there are several machining techniques like turning, drilling, shaping, planing, and also milling, so on, broaching, etc. So, if we talk about the classic case of turning, so then we can classify it as orthogonal and as well as oblique turning. So, we can classify in terms of the angle of the cutting tool in with respect to the workpiece. So, when the tool is placed at 90° with the center line of the workpiece, then we can call it as orthogonal machining. When it is kept at an angle, then we can call it as oblique machining. So, so also there are several kind of chip formation mechanisms which can make the machining also a very interesting manufacturing technique. So, a high amount of mechanics is involved in case of machining processes. So, like in case of ductile materials, we often come across the built up edge formation. So, it is basically it is the when the chip is formed. So, when the tool acts, this chip getting soldered over the tool and it makes the tool front as blunt, and also it is also makes the built up edge formation. So, it is often a phenomena that we see in case of ductile metals, and then it also impacts negatively that it hampers the surface finish of the machine part. So, likewise in case of brittle materials, we often fail to get continuous chips, rather we can get discontinuous fragmented kind of chips of irregular geometries. So, so this is so based on the the material properties which is undergoing the machining processes, we can see several differences in the chip geometry and the microstructure formation in the chips, and also the microstructural evolution at the machine surface and the surface finish. So, we will go into the deep later towards the end of this course. So, for now we will just discuss briefly about the variants of the material removal processes. So, I already told about turning. So, turning generally we do it in a lathe. So, here basically the workpiece revolves around a central axis and the cutting tool basically moves along the length with a preferential feed and depth of cut, and we get chip formation, and thereby we basically reduce the diameter of the solid ingot. And then number 2 is drilling. So, it creates cylindrical holes in a workpiece using a rotating cutting tool, that is drill bit. And then there is shaping and planing. So, basically shaping and planing, they are exactly opposite to each other. So, in case of shaping, the tool which is which undergoes reciprocating action and the workpiece is fixed, and in planing it is exactly the opposite, where the cutting tool is fixed and the workpiece mounted over a table, it reciprocates back and forth, and thereby it undergoes the material removal process. And then milling. So, milling also there are several classifications of milling, like surface milling, gang milling, and also slab milling, etc. So, we name the milling process accordingly based on the where from and how we are basically removing the material. And then there is a grinding. Often grinding is used as a process which is a finishing process post the conventional machining routes. So, basically in this case a rotating abrasive wheel we generally use to remove the material and achieve fine surface finishes. So, I mean, surface grinding, or there are several grinding variants we will learn later on. And then there is broaching. So broaching is a so in case of broaching, we used a tooth tool broach which removes material. So generally we do it in case of hollow shafts. So in this case you can understand, this is the a hollow shaft where we can put the broaching tool inside, and which is capable of the finishing process, and also making the through or blind holes in case of circular cylindrical cross sections. So often we do the broaching operation by mounting the tool over a lathe. So this is the about broaching. And then sawing, it is one of the simplest manufacturing technique or material removal technique that we know about. So in this case, material is removed by a tooth saw blade to cut the workpiece into desired length or shapes. So the key characteristics of the material removal processes are, so it achieves high dimensional accuracy and good surface finish. Output, so it generates precise shapes, contours and geometries. And but one thing should be the main drawback about the subtractive manufacturing processes, for example machining, is that we often end up wasting a lot of raw material. So for example, in some of the critical safety critical application like space, defense, for just for an example, we can some often engineers start with the initial dimension of say 500 mm to develop a part having end dimension as 50 mm. So it is a lot of wastage. So that wastage can be taken care of by applying additive route in place of subtractive routes, which we will discuss next. But before going to additive manufacturing, the route to additive manufacturing is basically established by powder metallurgy. So what we will discuss powder metallurgy in the next class. So so we are stopping today for this class. So see you in the next class. Yeah, bye.